Arriving here in section 5.2.2, we are ready to define exponential functions. Here is our formal definition. An exponential function takes the form f of x equals a to the x, where a is greater than 0 and a is not equal to 1. In our exponential function, we have two parts. This part A is called the base, and what's important to recognize about an exponential function is that has to be a constant, a number like 2 or 3 or 5, something like that. So we have a constant base, and the superscript here is the exponent. In an exponential function, that's where we place the variable. Now we have a couple of stipulations on the base. The base A has to be positive, and the base cannot be equal to 1. If the base is equal to 1, and we look at a function like this, 1 to any power is always equal to 1, so it's not quite an exponential function, it is a constant function. So we're going to exclude 1 as a potential base. Also, we want to make sure that our base is positive. If we take a negative base and raise it to a power, well, if x is even, we're going to get a positive output. If x is odd, we're going to get a negative output. So you end up with a function that oscillates above and below the x-axis. But if you have a positive base that's not equal to 1, you end up with an exponential function. Now, we've got two types of exponential functions that we're going to look at, and I'm going to give you a quick sketch of the graph. We'll analyze this in much more detail in a later section, but for now, this will help you to get a visual on what an exponential function is. If our base A is greater than 1, the function is increasing. So the picture of our function is going to look something like this. This is an example of an increasing exponential function. An exponential function starts out growing very slowly, and then it grows at a rate that is almost unfathomable. An increasing exponential function is used to model cell division, compound interest, population growth. Here's one that's interesting, the spread of a virus through a community, for example. These start out slow and they compound or grow incredibly fast. If you think about cell division, whenever a cell, a living cell, goes through its mitosis process, it divides and makes two new cells. Those two new cells make two new cells themselves, and this process continues. Whenever a child develops in its mother's womb, it starts out as a very tiny cell and grows to trillions of cells in a very short period of time. That growth is called exponential growth. Now, if the base A is a fraction between 0 and 1, that's what we're looking at here, a fraction, then the function is decreasing. So it has a similar nature of the first function we looked at, but it decreases very quickly. A decreasing exponential function can be used to model radioactive decay. So if there's some sort of radioactive accident, the radioactive substance decays very quickly at first, and then it levels out and slows down over time. So you have a steady state amount of radioactive material in the atmosphere. Maybe you've heard this in a physics class applied to Newton's law of cooling, or loss of memory over time. For example, your memory fades very quickly at first and then steadies out over time. This can also be used to model a decreasing population. An increasing population would look something like this, but a decreasing population can also exhibit exponential decay. Exponential functions are very fundamental and important to the world around us. For example, if you have a savings account, or maybe you're interested in opening a retirement account when you get to work, understand that your money grows exponentially. So it is possible to save a small amount each month at compound interest and have that money increase exponentially so you have a nice retirement fund. All of that, your car payment, your house payment, all of those important things affecting your everyday life are based on these exponential functions. So it's nice to have a working knowledge of this framework that is out there in the world. Now, I want to point out something important here. We have dealt with exponents all semester, right? So let's answer this important question. How is an exponential function different from a power function such as y equals x squared? Y equals x squared is a power function, right? It has a base and an exponent, but this is not an exponential function. This would have been, think about our parent function y equals x squared. This is a power function or a degree 2 polynomial function. Notice here the base is variable and the exponent is constant. So in order to avoid calling that an exponential function, we call it a power function. We're recognizing there is an exponent there, but I don't want to call it an exponential function because technically it's not exponential. Think about the shape of the graph of this power function. I know you know it very well. The shape of that graph would be a parabola. It doesn't look anything like the two exponential functions over here on the left. The base is variable, the exponent is constant, so it does not qualify as an exponential function. But if I switch those two positions and I consider the function 2 to the x, in this case, notice the base is constant, not equal to 0, not equal to 1, greater than 0, and the exponent is variable. So we end up with an exponentially increasing function. So the graph of this would level out and then it would grow very, very quickly. So an exponential function has a constant base, variable exponent. Then it qualifies to be a very important exponential function.